everyone. My name is Phil Bedard. I'm a principal engineer here at Cisco Systems. I'm here today at NANOG 84 here. I've done a couple other NANOG presentations in the past, but today talking about SDN, or software-defined networking, or SP networks. And this is kind of a 2022 edition of this. SDN's been around for quite some time. This is a bit of an update on kind of what's going on in the industry and the overall landscape with SDN today. We'll go ahead and get started. Brief agenda. It's not a complicated agenda today. It's really, what is SDN? I think most people understand what SDN is, or at least have heard the term over the last, 18 years or so since it originated. And then we'll talk a bit about, what is an SDN controller? Like, what is the element that's actually enabling SPs to, do SDN in their network today? What are the standards and industry initiatives behind those? And like I said, we'll take a look at these, the implementations that are out there today, all the groups and all the standards that are going into, how SPs might use SDN as it's currently, looked at in the industry. We'll touch upon a couple of network use cases. These aren't new use cases. They're problems that SPs have had to solve for quite some time in their networks. But we'll take a look at how we can use sort of what we call an SDN controller to really enact those changes in the network and sort of the standards and data that goes into that. Obviously, SDN is kind of a loaded term. People overuse the term SDN, and they have for many years to mean different things. So we'll kind of go ahead and look and give a little bit of background to SDN. And this is really kind of maybe what it means to me and how I've learned, to grow or love or hate the term SDN. And first of all, a little bit of background is, what do we consider a non-SDN network or a non-software defined network? And really for SPs, that's 99% of networks that are deployed today and have been deployed for many decades. This is a network where most of the intelligence and the control plane is embedded in the device and the device level software. These are our traditional IGPs, so things like routing protocols distribute routes end to end. And then in turn, the device has software that installs, forwarding information. I think most people are really familiar with how these networks work today. And it's not to say that these networks aren't intelligent. We've added through standards and extensions over the years, many different things to enhance the intelligence of the protocols and really the embedded networks themselves and the control planes. When you look at things like RSVT, and what we're doing with that, segment routing, even things like BGP flow spec, they're really adding intelligence to the network and more capabilities. And if you look even at an application like auto bandwidth, which is deployed in a lot of RSVT type networks, that's really, you can consider that an SDN application. It's really an intelligent application that's taking in information from across the network to make more intelligent path routing decisions. But it's still limited in what it can do, being embedded into a device and the capabilities that mainly based off of the data that it's able to consume and make decisions on. When we take a look at SDN, or software-defined networking, I've got a couple different views of it that I'll present. Really the purest view, and this was the original intent of SDN, was to have an external control plane that's very intelligent, that's managing a set of relatively simple forwarding elements in the network. I think everyone who knows the history of SDN is familiar with OpenFlow. OpenFlow is really a construct to implement a strict forwarding on a device level basis. And the idea was I would have this brain or control element that was forwarding the end-to-end paths for applications or just routing across the network. That didn't really come to fruition. I think that what people wanted to do with SDN was a noble goal, but there were a lot of gaps. In SP networks, just things like local protection and rerouting traffic when failures occur. Being able to handle those in a quick manner is difficult with a centralized control plane. So we still needed a distributed control plane to really handle, some of those use cases. What it did help with, though, is to define what we call standard interfaces for how we talk to devices. Standard languages for how we describe, forwarding constructs. OpenFlow is kind of the initial one. P4 has emerged more recently as a way to do that, and it's widely adopted for a variety of use cases. So SDN has brought some benefits and getting people to look at how we can be more programmatic on how we manage these networks. My take on SDN is something that I really kind of call hybrid SDN, and I'm not the originator of that term. And it's really a more pragmatic view of where we're not, discarding the intelligence that's in the distributed control plane today. It's really enhancing that with additional capabilities that are difficult to put into a device level software. So it's really about augmenting different layers of the network, whether it's the service layer, the traffic forwarding layer, or the routing layer that drives that. So like I said, it's really about enhancing the network and enhancing what's done today. And I think when we look at what most SPs want to do today, that really fits in that story. A very simple example of something that some people do today, those that are familiar with path computation elements that help to manage traffic engineering paths end to end across the network. A PCE is you could consider that a form of SDN control in this hybrid network, because I'm using some type of external data or constraints to add intelligence to a distributed network that's running traditional protocols. Something that often goes hand in hand and is also kind of a buzzword in itself is this idea of intent-based networks or intent-driven networks. Like I said, you often hear this sort of hand in hand when someone talks about SDN, and a lot of times it is just sort of a buzzwordy term. Really, the whole goal, though, is to move to what we call more declarative, simple configurations to drive more complex network functions. And this comes more into play when you talk about multiple SDN controller elements talking to each other. The idea is to abstract a lot of the complexity of the underlying network from the upstream controller and really allow the controllers that are managing more complex parts of the network to decompose those instructions into something that's can be configured on the network directly. Like I said, it's all about abstracting sort of complexity as you go up layers in the network and being able to have like a simple call like I need service between A and Z at say an OSS layer of the network, and then have something intelligent underneath decompose that into the more explicit configuration versus that upper layer having to know how to do that across say multi-vendor networks end to end. I've mentioned the term controller a few times. A controller, when we looked at the kind of purest view of SDN, that is the external element that's helping to control the network. The definition of controller, it's simply something that directs the actions or functions of something. In this case, it's the network, it's network devices, or it's potentially other controllers. Because we can have controllers, as you'll see, at a hierarchy, and that really lets us build a more kind of scalable solution in how we enact SDN on the network. There's some key components to that. Obviously, on the southbound side, I have to talk to the network elements, and that's through a variety of protocols today, both open and proprietary. And then I have to aggregate that data. If I really want to deploy this in a multi-vendor network, we have to normalize that data from different vendors into what we call standard models, and I'll present a little bit about that later. But this is really key to how we have good interaction between different controllers and be able to make this sort of a more multi-vendor open way of managing the networks. The other part is rendering northbound interfaces. I talked a bit about abstraction, and the idea of sort of a low-level controller is to abstract the network from a higher-level controller. It has to be able to put that in a format that it can consume. And there are standards and there's initiatives today where a lot of that's being worked on to make this a more multi-vendor interoperable type of architecture. And really, SDN is about intelligent applications. It's something that either has to make the network easier to operate or enhance some type of functionality. So really, that's the key goal of that. Otherwise, why implement something like software-defined networking in the beginning? Well, like I said, and most of this, as I talk about it, really is around the hybrid SDN view, where I'm not throwing out the existing network. It's really about adding functionality and covering specific use cases to help sort of enhance services or the infrastructure itself. So why use SDN? And this is sort of the age-old question of, what is it buying me? Is it helping me, save money or make money in some way? Sometimes it comes down to that. There's a variety of use cases today. Really kind of the definition view of it, really it's enhancing the network. these SDN controllers and SDN in general, the idea is to take in data generally that's not available in a distributed control plane, and add intelligence to what's going on in the network. We've done a lot of enhancements, like I said, to add intelligence to device level software and standard routing protocols. At some point, that becomes difficult. Obviously, all SPs know it's difficult to upgrade software on devices over time. We've made that easier by having some application independent upgrade processes, but still, it's very difficult to do that end to end across the network. It's very painful. So really, SDN allows us to have, I'll say, a more modern sort of application delivery outside of the device. And the interfaces to the device stay standard. They don't change very often. So really, I can rebuild that application as needed without touching the device itself. I'll talk a bit about multi-layer networks. And when I talk about multi-layer, typically I'm speaking about IP and optical networks. And if you've seen SDN presentations in the past, many of them cover how we better manage IP and optical layers together. There was a lot of work put into like GMPLS, and GMPLS was a device level protocol set of standards that were meant to really marry together IP and optical and be able to exchange data between the two, make intelligent decisions. After many, many years, it really never took off, just due to a lot of interop type of issues, even though these are standard protocols. I once called SDN, it's sort of the savior of that, because really you're just kind of punting the intelligence upstream, and I'm able to handle these multi-layer networks at the SDN controller level, and not necessarily between two devices themselves. Obviously optimizing network resources, that's sort of a boilerplate reason to run things like SDN. There's a lot of ancillary benefits in things like network visibility, and that's mostly due to the amount of data that I'm getting from the network. In the applications that the SDN controller runs, really allows me to analyze and inspect that data and get more out of the network. Like I said, if nothing else, it's going to enhance visibility by doing a lot of data collection for the network itself. Who's using SDN today? I'll say even today, very, very few people are using software-defined networking, especially in SP networks. You've seen papers and maybe some NANOG presentations from content providers, and those that are doing a lot of egress traffic steering of BGP controllers or routing controllers that they're using end to end across their network. Those are a bit advanced, and obviously there's people doing it. The amount is pretty low. Most SPs are looking at more what we call this hybrid SDN model. And on the bottom, this is, if people haven't seen it, this is kind of the Gartner hype curve. And definitely SDN went through its eras or multiple eras of this sort of peak of inflated expectations. And sort of disillusionment means that nothing's really happening with it. I think we're at a point now where we're starting to see more initiatives around SDN and SP networks, where we're kind of on the upstream or the upswing of the sort of enlightenment phase. We're not quite to a productivity phase yet, but I think we're somewhere on this line or trajectory up now, mainly driven by a lot of industry initiatives around SDN that have come to life in the last few years. So I'll spend a bit of time talking about kind of standards and initiatives that are going on right now. Key to this, I talked a bit about multi-vendor. And to drive multi-vendor, we really need interop between these different controllers, between the different elements. And there's been a lot of push towards standardizing a lot of that in the last few years. We need a standard kind of architectural definition, kind of roles and responsibilities of what different controllers do in the network when it comes to SDN. And the thing that's really helped, drive a lot of this standard data models. Yang, I think most people are familiar with Yang at this point. It's the de facto standard of how we model data at the device level, the service level, even how we describe network topologies, and I'll show that in a bit. And it's really necessary to normalize what's often proprietary network data into vendor agnostic data, so that we could share not only to applications within an SDN controller, but also to other controllers themselves, and also protocols, standard interface protocols on how things interact. And the models drive the APIs. Really. So the standard models drive standard APIs. Having standard communication protocols is also key. At the device level, we have NetConf and things like GNMI that have seen a lot of traction in the last 5 to 10 years now. NetConf is obviously widely implemented on these vendor devices today. From controller to controller, RESTConf is really the de facto standard. I think everyone is kind of coalesced on using that. It does have some drawbacks, but it is sort of the standard, and it's the way that controllers communicate between each other. So I mentioned having an architectural framework to really build this, SDN controller architecture. And some of that's being driven by the IETF and specifically the ACTN working group, the Abstraction Control of Traffic Engineered Networks. And they've defined RC 8453. And really, it's a loose framework of controllers and how SDN works. And what it really allows you to do is move away from sort of a big monolithic type of piece of software that's controlling many different network types, different domains, and breaks that into more easily consumable smaller controllers that are responsible for just their own specific task. So you'll often see these terms in the ACTN framework of like an MDSC. You'll see that called a hierarchical controller in other text. And this notion of a PNC is really similar to a domain controller. It's what controls a specific domain of the network that it has some sort of technical knowledge of. So it's the lowest layer controller that's actually talking to the network devices. So we talk a bit about roles and the roles of the different controllers. The CNC or customer network controller, that's an OSS BSS system. It's often an orchestration system or a workflow manager. So that's where you want to abstract, most of the intent to. So like I said, if you have a service that says, I just need a VPN from A to Z, that's the type of function call it would make to a multi-domain service controller, which then is broken down into more consumable bytes and then sent to specific provisioning controllers. So like I said, the HCO or the MDSC, it aggregates information from all the domains, so it can make intelligent decisions. And like if it does get a request for a service from a CNC, it's able to decompose that into its constituent parts and send it to where it needs to go. For example, an IP plus optical provisioning operation would be handled by an MDSC. The provisioning network controller, like I said, that's really, it uses its SBI to connect to the devices themselves. It could be other controllers as well. There's no strict hierarchy with this. It doesn't have to be 3 layers of controllers. You can have many different layers of controllers that interact and communicate with each other. And ACTN doesn't specifically define the protocols used between the controllers and the interfaces. Like I said, it's more of this sort of loose architecture of how they should communicate with each other, but not the underlying low-level protocols and things like that. What else is the IETF doing specific to SDN? We talked about you really need standardization at every level. So the L2NM, L3NM, those are standard network models for VPN configuration. So it really gives a vendor agnostic way to describe VPN services. And then it's up to the controllers themselves to translate that into device level configuration. So we've seen a good adoption of these models. Like they still have some gaps that need work, and it would be good for more operators to be involved in those efforts. There's also been a lot of work done in the last 5 or 6 years around network models and how we describe networks. And this really comes into play when you talk about controller to controller interaction. And I'll talk a bit about that coming up. And then really continued work on all the protocols that sort of enable SDN. These are the standard interfaces to the devices and to the controllers. The ones I list here are more device level standards, but enhancements to PSEP, continued ISIS and IGP extensions. BGPLS is an important one because BGPLS is a common kind of de facto way that I learned topology information from a network. And then things like network telemetry framework to create more standards-based ways to get performance measurement data off the network. Another group that's really driving these SDN standards that I would say doing a lot of work currently is the ONF TIP project. So it's the Telecom Infra project. So ONF is Open Networking Foundation, and they have a number of different projects, and then under those have a bunch of different groups. And specifically, this is the OOPT group. And then even another consortium under that is one that we call MUST, and For short, you just kind of call it TIP must, and it stands for mandatory use case requirements for transport SDN. What they're really focused on is defining like the SBI, the NBI protocols and things. So this is where operators are trying to define some of the low-level constructs that are used for SDN. And it really gives guidance to those in the open source community as well as vendors on what they should be building as a controller within a controller. They're also defining use cases. So a use case might be provision a VPN from A to Z, or provision an optical circuit from A to Z. So they're defining those use cases and those workflows. So if those that are building the controllers want some guidance on what they should be building, what operators are looking for, that's what this group is trying to define. And this group is driven by operators. There's no vendor participation in the must group. And as of today, I think there's 10 different operators that are involved, but definitely if others want to get involved, simply reach out to that team. Always looking for more involvement. And they've when I talk about SDN architectures, they've defined their own architecture, but as you can see, it looks almost identical to the ACTN architecture. Some of the names are a little bit different, but that's for a reason. We want to coalesce really on one type of SDN architecture for networks, specifically SP networks. So like I said, a lot of similarities to what you see with ACTN and how they define the controller interactions. So we talk about, and most of that covers both IP and optical. When we talk about the architectures that are involved and how we define that. And the TIP must, they're working on use cases for both IP and optical. One thing that I want to mention, specific in ONF as well, in the OTCC project, is the Transport API, or TAPI. And it's a little bit different. TAPI is a set of Yang models that really describe all of the functions I need to manage an optical transport network. Optical transport networks are traditionally very proprietary. There's no real device level interop with optical networks like we have with IP and routers and switches. They haven't, GMPLS exists, but it's not really interoperable between vendors. There's a lot of secret sauce that happens. So TAPI is a way to standardize a set of models that really is rendered on the northbound side of a controller. And it abstracts all the functions to manage those networks. And really, TAPI has seen very widespread adoption over the last 3 or so years. It's really come to a point where almost all of the optical vendors have a TAPI-based controller that can be used to manage their networks. There's still differences in those that have to be worked out, and there's still some gaps in TAPI, but it's been a really good initiative to sort of coalesce the industry on a single sort of standard set of models for how we manage optical networks. And there's also been, interop events, and you can find information that, say, the OIF has done specifically with TAPI interop events. And it's referenced by these groups like TIP must, who's, defining some of the low-level interactions. They're using TAPI to do that. So definitely would look into TAPI and the things that are being done with Transport API today. It's a very simple example of a TAPI connectivity service. And this is an example of like a wavelength service across a DWDM network. Everything in TAPI is hierarchical, like most networks. Optical networks are built in layers. So TAPI has a way to describe, each layer as well as the interconnections between those layers. It's a quick example of a TAPI to create that last service. Like this is what a TAPI REST call looks like. It's more for looking out later. TAPI is quite complicated at times. It's definitely not meant to be human-driven. A human would not write one of these types of requests. It's really meant to be consumed by controllers and driven by controllers. So one of the key parts to these SDN controllers is really data ingestion. Data ingestion is what's needed in order to enact changes to the network. It's sort of table stakes for what SDN needs to do. It needs data from the network to make its applications more intelligent and to make decisions. And I kind of separate this between packet and optical. Like I said, this is IP and optical. That's really kind of the drivers for what a lot of folks are doing in SDN today, at least within SP networks. So really, I need topology data to make routing decisions. I need topology data as well as say performance metric data off the network. And I'd say the industry is within the last few years and probably even longer now, 5 or 6 years, has really driven to a set of standards, and they're more de facto standards. than really hard and fast standards. But BGP-LS is used. So those that aren't familiar with BGP-LS, it's BGP link state. It's a way to translate IGP data into BGP NLRI, which just makes it easier to package and for an external system to consume it, rather than trying to participate into the IGP itself. And then PSEP, this is a path computation element protocol. It's really the de facto standard for how we get traffic engineering information off the network. So PSEP on a device has the ability to report LSPs that are going through that device, or it's the head end for. So if you look at sort of IP controllers or packet layer controllers that vendors have built or even open source, they always include BGP-LS and PSEP components to it. There's still a lot of direct device interrogation for getting data off. Either CLI screen scraping, SNMP. Not everything is available in standardized protocols that you might need. So when you talk about a domain controller, it might have different ways, but the key is that it needs to expose that northbound in a standard interface. So when we look at controller to controller interaction, that's really sort of key. And we look at topology information, which is, like I said, sort of table stakes for doing this SDN control. The IETF has defined a lot of RFCs around a standardized network model. And there's a base model in RFC 8345. And there's a number of RFCs and drafts that build upon that. So they add data to the base network model, which may just include, say, node information. So if I want to add TE information, L2 information, even segment routing information, there's other drafts that now add information to that. We also have TEAS models that describe in great detail traffic engineering networks. And there's also hooks between the TEAS models and the standardized network models so that we could combine a really rich combined network model. And I think what you'll find is, most, like I said, most IP controllers have kind of coalesced on these models in order to describe and consume network data. Just for reference, is what the RC 8345 topology model looks like, with a couple of nodes as well as a couple of links. And this uses both L2 and L3 extensions as well as the SR draft extensions for the network model in order to describe a IP topology. And typically, this is being consumed by like a hierarchical controller or even an OSS BSS system. It just depends on the use cases involved. In many cases, you also need metric data. This is what I call metric data, which is really interface stats, flow data through like NetFlow or IPFix. If you want to make, even really application level traffic decisions across the network that you're trying to control. And like I said, that metric data is overlaid on top of the topology data or TE data even. It really gives you a very powerful, way to build an intelligent application for traffic steering and other types of applications. So we look at network data on the optical side. So the controller to the network, that's still very often proprietary. It might be TL1, in some cases SNMP. Some vendors have moved to even using things like netcount. But typically all the encoding, the models that are used. On the IP side, we have a lot of standardized models for device level interaction, either through IETF or OpenConfig. With the optical, the device level is very proprietary. And that's the reason why the controller to controller, is so important, because it's really rendering that proprietary data into something that's normalized. It's standard across different vendors. So something like the inventory from an optical device looks the same in TAPI, from one vendor to another vendor. That's really the key in making this interoperable and being able to build sort of a multi-vendor open SDN architecture. Like I said, TAPI is the de facto standard. There's a number of models that are used to describe both the hardware as well as the topology that's created, as well as the services that are created over that. So like I said, it's quite rich today in what they've built. And like I said, there's a number of implementations of it already. Yeah, so we've talked a bit about network data and how network data is consumed by this hierarchy of controllers. In this case, you can see this is just kind of a graphical view of what I just talked about. So, the optical domain controllers, and, this is where I'm using typically proprietary methods to get that data. And then the IP controller, like I said, we're more standardized on the IP sort of router switch side of how you get data off the device. Not always, but in many cases, we have more options than on optical. But the key is, what gets rendered northbound of those controllers is all standardized data. That way, the hierarchical controller, or HCO, it could be from different vendors that are consuming that data. And the applications on those controllers that are able to use the data in a normalized manner, no matter where it came from. So where do we have standards gaps with this? I would say most of the gaps are on the IP side. The good thing about TAPI is TAPI really kind of covers just about everything on the optical side, from topology, equipment inventory, fault data. We have good topology data on the IP side, but that's about it. When you talk about physical inventory, and this is really controller to controller. We spent a lot of time and effort in the IP world on standardizing device models or device level models. We haven't done a lot when we talk about, controller, IP controller to say HCO models. So there's still things like fault data, physical inventory data, and recently a draft was introduced, and it says optical, but I think it'll be expanded to cover, packet layer devices as well. And it's really just a way to aggregate data from multiple devices into a single model that can be exposed northbound to different controllers. So like I said, in the IP world, we've got a few gaps that I think need to be solved in order to make that more applicable. Just a couple statements on open source controllers. We see more and more vendor controllers, and I think if you look at sort of the leading 3 or 4 equipment vendors, they may have HCOs. They probably have domain controllers specific to optical and IP, if those are equipment that they supply. There's a lot of open source controllers as well. The 2 really kind of popular ones, and I think people have probably heard about Open Daylight as an SDN controller. It's been around for quite some time. It's a Java-based system. It's very plug and play, and it's got different use cases and different applications that it's solved over time. It still remained the base for different open source as well as commercial vendor controllers. So really, it's a framework for building applications and sharing data between those applications that enables these SDN apps to run in the Open Daylight architecture. ONOS, Open Network Operating System. That work also started 10 plus years ago now, is now part of the ONF. Very similar architecture to Open Daylight. They have progressed. There's a microservices-based version of ONOS today, and they're tackling a wide range of use cases. I'll say the development, ONOS is probably there's more people working on ONOS today, as well as modern use cases around 5G, BNG, or Open BNG. So there's been actually a lot of work and even some actual production implementations of things that are done with ONOS. So definitely would take a look at that and the initiatives that they have and see if others want to get involved in those. So we'll talk a little bit about network use cases, and these are SDN use cases. They're not new use cases, but they're things that can be solved in a better way, typically with some type of external controller or SDN control. Outside of what you're doing just in the network itself. At first, though, I'll talk about sort of real world view of where people are with SDN controllers today. And this plays a part in sort of use cases in how you solve problems with SDN today. You really consider the controller as part of the network. I think that's a good way of looking at it. It's really part of the network control plane. So the applications that are built are meant to be real-time, sort of closed-loop automated, control applications when it comes to things like traffic steering or resource steering in the network. I think when you look at so some applications, they're not necessarily closed-loop applications. A lot of them are visibility-based. Things just making it easier to manage the network through data collection, and kind of this is the first entry point we see for SDN controllers, or what you would want to call a modern SDN controller, especially in SP networks. It's starting with visibility. It's really bringing data into the network. And I think, as I mentioned earlier, there's a lot of benefits in just the visibility aspect of bringing the data into a single sort of repository. And then if you're feeding that into an HCO or a hierarchical controller, then you get good view of that data across multiple domains. So you get things like fault correlation that maybe you didn't have before because you didn't have all of that data in a single repository, or a set of applications that could look at data from multiple domains and be able to make some sort of intelligent decision or correlate some type of fault between those domains in an intelligent way. Like I said, fully closed loop automation, that's still pretty rare. Although that happens in our distributed control planes today, not a lot of people trust the centralized box to make those types of decisions. So often what we see today is more of like a recommendation engine. So I say, speaking of our deployments and what we do, the real SDN control type applications usually they start with a recommendation, and then there's a button for someone to push or something for them to enact a change on the network. Fully closed loop, we're not quite there yet for the majority of service providers. So one use case that's sort of near and dear to me is this notion of shared risk link groups. And like I said, a lot of the SDN applications that we look at today talk about multi-layer networks with IP and optical. And this is definitely an IP and optical type of use case. So typically at DWDM networks today, we have multiple wavelengths. There could be multiple IP interfaces that use the same path of the network. And we don't want to, step on those, two interfaces that are using the same DWDM link. So you don't want, say, one interface protecting another interface that share the same fiber. Fiber cuts are by far the most common type of failure in networks today. So for certain services and interfaces, you don't want to protect one using another over the same fiber or conduit or node. And we seed information on the IP networks traditionally with SRLG data from the optical network, but it's quite cumbersome in many cases to get data off the optical network and correlate it with the IP network because we don't have a good way to share that information between the two different systems. GMPLS has solved some of this, but it's a very vendor-closed solution. You can't, hook up a GMPLS router from one vendor and a GMPLS optical node from another vendor and have this type of sharing takes place. They've been vendor proprietary solutions, and even those solutions are not widely deployed at all because they're quite complicated. Yeah, so we look at shared risk link groups or SRLGs. The use case is really where the IP layer, it needs the optical layer information for things like protection diversity. And to be honest, it's just an easier problem to solve by sending all of this data upstream to a more intelligent, call SDN application. So it can dynamically learn what's on the optical network, and then it can seed the IP network with that information. So if it dynamically changes, things like optical restoration. So optical restoration changes the optical path dynamically. And if the IP layer is unaware of that, and normally it is unaware of that, then the data that it has about shared risk is already out of date. So one very simple application is being able to take all this data together, correlate it, and then seed the router with updated information almost in real time as it happens. And this is an application that's been looked at for many years when it comes to using SDN and SDA controllers and getting data off the network. But like I said, this is one very simple common use case that could be solved with an SDN controller. Another common use case is just traffic balancing. This is really more of a BGP, eBGP external edge traffic balancing use case. And when you look at the SDN-like controllers that have been built by content providers, and others probably more on the advanced stage of automation, they've definitely have solved this use case over time. Another use case is edge traffic balancing, and this is a use case. It's been solved over time by different content providers. There's systems that they've published white papers on even that describe how they do this in a really an SDN controlled manner. And a lot of that, in a true SDN sense, it's really about using network data to make those decisions, and not just standard network data. Like I said, the real benefit to an SDN application is being able to consume more granular data or things that maybe you just don't even get off the network. Maybe there's things like cost maps that come from another source, geographic maps as far as routing people to a specific location. Like I said, those are very common content provider or sort of request routing type of decisions. But enacting those into network routing and network forwarding, that's where these SDA controllers come into play. So this case is a simple where I have traffic that I really have my intent, and if it's really an SDN based application, I want to give it my intent is to balance traffic across all of these peering connections. And in normal BGP, and this is outbound traffic, which is a bit easier to control. But in normal, say BGP, that that doesn't happen. There's other things that are built in BGP that steer traffic a specific way. But I want to take all this data, and then I want to make an intelligent traffic routing decision. And like I said, really, it's the job of the controller is really to decompose that ask or that intent into the specific actions on the network. And that's really where the real intelligence on SDN comes into play. Like I said, this is a use case that's it's been solved in other ways over time, but we do see more and more controllers that are able to take care of this type of use case. Like I said, these are just a couple of use cases that SDN could be used for. There's a lot of more advanced traffic routing, traffic optimization use cases. So the key is being able to take data, not just from the network, but from other places as well, and collate that as well as multi-domain or multi-layer information to make a more sort of intelligent decision that can't be made by just the on-box control plane. And that is it for me. This has been my session on SDN and SDA controllers. And I realize it's a bit on the high level side of things. But really the industry initiatives and the industry push for this, I encourage folks to get involved in that. Take a look at that and join groups like the IETF, the TIP working groups. If you have SDN use cases that you would like to see have broader coverage of, I definitely, like I said, encourage you to join those industry groups. But from that, thank everybody for your time. I hope you enjoyed the session and enjoy the rest of NANOG.
Hi, Phil.
Hopefully I'm here. Hey, everybody.
You're here. We have somebody walking up to the microphone now. Please state your name and organization.
Is this Mike? There we go. Hi, Chris Woodfield with Twitter. You mentioned OpenFlow very early in the talk, and I got the impression that you were referring to it in the past tense. Is that still a relevant protocol, or has it largely been supplanted by the newer protocols you've mentioned at this point?
Yeah, I think it's been largely supplanted. I'm not going to say OpenFlow is completely dead and has no use cases. I would say in the SP context, it probably has even less use cases than in what we see in data centers. But I do think modern, more flexible ways of doing programming. P4 is very low level, but like I said, OpenFlow had a lot of good ideas. OpenFlow version 2 kind of improved on that, but as an industry, it has just not seen widespread adoption. No.
Okay, thank you.
Okay, thank you, Chris. We have one coming in from the outside, from Randy Bush. High level, could you relate these 42 complex mechanical protocol IETF-ish approaches to the forever work in progress on the network as a program magic of McCowan, Rexford, et al.? It seems a bit of software implemented network and missing some abstraction to be software defined as opposed to hacked. Aren't we still using tweezers?
Yeah, I think that's a lot to unpack. I might need you to repeat that one a bit, but I think it's just the complexity of what's still there. And still Randy, if I'm completely misconstruing this, let me know. But the idea, it's still complex, and it's still a lot of string and glue that is kind of binding these things together. I think the one thing that we have a bit more of today is less IETF heads. I don't want to say that in a bad way per se, but people driving this, and that's where I think the operators that are driving it and trying to drive the abstractions, I think that's really key. Otherwise, we're just kind of back in the day of what we call automation, or we just use this blanket term of automation in SDN, and it's still super, super complicated. But sorry if I'm misidentifying that, but contact me offline if you want me to address it in a different way. Okay, thank you, Phil. Randy, hope that solved it for you, and hope to see you in person again sometime. So thank you for your presentation. We're out of time on that.
Yep, thanks everyone.